The periodic table, a symbol of wonder and truth in the science world. We already know how certain areas in the periodic table have similar physical characteristics. Copper, silver, and gold, for example, are in the same group, and they are all good conductors of electricity, and they are metallic shine. But what if, deeper down to the atomic level, what are some characteristics that tend to show up in certain areas of the periodic table?
Well, we'll find out when we dive into the periodic table.
First of all, what are atomic characteristics? Well, they are merely the small details of an atom, how big they are, how easily they can take or give electrons, and even how they will react when presented with other atoms.
Alright, so let's start off with atomic size. So, as you can see, we have a periodic table, fantastic. So, as you go down the periodic table, the elements get larger in general, just because there's more protons, more neutrons, and more electrons. But as, kind of more interestingly, as you go from left to right, it gets smaller. This is because the right side has more protons, so then the electrons are pulled into it more, while the left side has less protons, so then the free electrons are able to move around more.
I'm a cation, which, if you think about it, cats make you positive because they make you happy.
I'm an anion. If you think about it, anion sounds like onion. Onions make you cry, so onions make you sad, negative.
Let's take the creation of table salt, as we are all probably familiar with it. Sodium is over on the left side of the periodic table, and it is the one that is giving away its electron, so it can be like a noble gas and have 8 electrons in its outer shell, when it usually bonds with chlorine. Chlorine on the right side is also trying to get 8, but it only has 7, so it happily takes the sodium's electron.
Sodium is now a positively charged ion, or cation, and chlorine is a negatively charged anion because they lost and gained a negative electron respectively. This trend of being a cation at the left side, and being an ion in most ionic reactions, goes throughout the periodic table.
Ionization energies, which really should be called cationization energies. It is the minimum amount of energy required to move the outermost electron from an element in its gaseous state. It is basically how much energy you have to put in it in order to strip away an electron. Sometimes they're easy, sometimes it is harder. The more electrons an element has in its outer shell, the more energy it is required to tear them away.
Also, as the shells keep getting larger and larger as they go down the periodic table, the easier it is to snatch up an electron because it is so far away from the nucleus. Here's an example of 2 sides of the spectrum. Cesium is near the bottom left of the periodic table. It has only 1 electron on its outer shell, so it is only 1 electron away from having the 8 it needs in order to be a noble gas. Or in order to look like a noble gas, that is. The shell is also very far away from the nucleus, so there is less attraction because it is so far away. It is like taking candy from a baby. Fluorine, on the other hand, has 7 electrons, so it is close to its dream of being a noble gas. It will want to keep all of the electrons it can. There is also only a few shells in its nucleus, so it will have a very large pull on the electrons because they are so close. Science.
Electronegativity. It is essentially saying how well the elements are able to attract electrons, basically a measure of how greedy they are. The differences between electronegativity will determine whether the bond is nonpolar covalent, polar covalent, and ionic. If one element is more electronegative than another, and they are in a covalent bond, the electrons will usually be near the element with the highest electronegativity. This usually results in a polar covalent bond. Like ionization energies, it starts out small at the bottom left, then grows near the top right. This comes in handy when looking polar covalent bonds.
Polar versus nonpolar bonds. In ionic bonds, elements completely take or give electrons, whereas covalent bonds share electrons. Polar covalent bonds are more ionic because there is a greater difference in the electronegativity. This will mean that one side of the molecule will be more positively charged and one side more negatively charged. Nonpolar covalent bonds are when the electronegativities of the atoms are the same, so that they share the electrons equally. To see where the electrons will be at, we just need to look at the electronegativity. If you have a water molecule Oxygen has a higher electronegativity, so the negative pole will be at the oxygen and the positive pole will be at the hydrogen.
Like this, for instance, just using Dawn dish soap and peppered water, you can make this happen. Science! First of all, we learned about atomic size, as it gets smaller at the top right, and then it goes larger towards the bottom left.
Okay, and we learned about positively charged cations and negatively charged anions.
Ionization energy, or the energy required to remove an electron, increases as you go this way or this
We
way.
then learned about increasing electronegativity, where it gets smaller at the bottom left, and then it increases towards the top right.
We then learned how electronegativity affects whether or not a bond is polar or non.
Science!